With the introduction of conformal radiometry, ASAP users now have the ability to calculate and visualize a number of radiometric parameters, including the incident number of rays, incident flux, radiance, and irradiance on a wide variety of surfaces in their optical system design, irrespective of shape. In addition, users can now also add arbitrary surfaces, including transparent surfaces, which can act to monitor the radiometric parameters at any point in the system while having no effect on the resulting ray trace. In essence, adding transparent detectors to the system geometry. We'll illustrate the feature with an example using a parabolic reflector and a filament source. The conformal radiometry feature can be invoked with a simple addition of the keyword bin to any surface or edge object within our optical system. If we run the file, we can see in our 2D view the parabolic reflector and the filament source as we begin to trace rays. The bin keyword instructs ASAP to calculate radiometric information along both the inner and the outer surface of the parabolic reflector. And that information is saved for later viewing in the 3D viewer window. Now within the 3D viewer window, we can see that initially nothing has changed. We'll hide our rays and note that we now have two new icons that have been added to the 3D viewer. We'll select the conformal radiometry rendering option and note that a number of new features have appeared in our 3D viewer window. We first note that a tessellated false color map has been conformally wrapped to our parabolic reflector. The coloring of the individual facets is determined by the number of incident rays on each facet as well as the facet size. And if we zoom in, we can see that we can click on an individual facet and immediately get information about the number of incident rays, the ray flux, the radiance, and the irradiance calculated at that particular facet at our prescribed wavelength. Now in this case, this information has been calculated using the local surface normal for the facet that we selected. And that's true for every facet in our 3D view. So this radiometric information is now being correctly mapped to the interior surface of our parabolic reflector using local surface normal information. In addition, we can see that we have a new toolbar which allows us to change the way in which conformal radiometry information is mapped into the 3D display. We can render the number of incident rays, the incident flux, the irradiance, and the radiance. And in this case, we'll choose irradiance and hit apply. And we can see that the irradiance is now mapped onto the interior surface of our parabolic reflector. We can map the false color in either linear or logarithmic space. We can also manually adjust the scale to provide a more uniform view in our 3D viewer. Now the second icon presents our conformal radiometry properties window. And we can see that a number of new features have been added, allowing the user more complete control over how information is displayed in the 3D view. We saw previously that if we clicked on a single facet, we could get radiometric information calculated at that facet location. We can also begin to calculate statistics for a larger and larger area of the surface using our slider bar. In addition, we have three default settings for the facet density that's shown, and our default here is high. If we wish, we can also specify the maximum facet length as a percentage of the overall size of the object. So in this case, let's choose a 5% setting, and we'll go to a slightly more coarse statistical average and hit OK. And we can see that we've dramatically increased the faceting level in our 3D view. If we once again zoom in on a particular location inside the reflector and click on an individual facet, we can see that we're now receiving aggregate information over multiple pixels at this surface location. We get an average value for the property that we specified, which in this case is irradiance, and we can see the minimum and the maximum values as well as the median, the mode, and the standard deviation. And we can get this information again for any local area of our surface. Another new feature is the ability to view all of the facet data in tabular form directly within the 3D view. We can see that for every facet shown, we can recover vertex locations as well as all of the radiometric quantities that have been calculated, including the incident number of rays, the flux, the radiance, and the irradiance. And if we click the irradiance tab, we can see that we have sorted according to that radiometric property. By selecting an individual row, in this case the maximum irradiance value, we can zoom in and see that the actual pixel with the highest irradiance value is highlighted in our 3D view. Now let's look at a more sophisticated example. In this example, we've created a compound parabolic concentrator that has been fitted over a model of a commercial LED having the well-known inverted pyramid structure. The LED die itself is surrounded by a spherical epoxy dome, and we can see the rays being traced as they come from the top surface of the LED die out from the CPC and through two detector surfaces. Now in this case, these detector surfaces have been made to be transparent and actually have no effect on the resulting ray trace, but are still capturing all of the radiometric information that we've previously observed. So in essence, they're simply acting like monitors to the rays passing through. Now we can also see the rays being traced from the side surfaces of the LED die. So we've now mapped the radiometric information that we calculated for this example into our 3D viewer. And we can see that one thing we didn't mention was that we added the bin keyword modifier, in this case, to virtually every surface in the system. And so that information has been plotted for all the surfaces that we see. Now we mentioned earlier that we added two detector surfaces, which in this case were defined to be transparent and therefore have no effect on the resulting ray trace. And yet we see that we have correctly calculated the irradiance at each of these two surfaces. Now if we look at our CPC, we can qualitatively see that virtually all of the energy coming from the LED die has struck the CPC interior surface at the edge toward the die, and we can see that we could very likely eliminate a certain portion of the length of the CPC without having any serious effects on system performance. Now if we zoom in on the LED die itself, we can see that we've actually mapped the initial radiance directly on the LED die surface, as well as on the bottom reflector sitting beneath the LED die. If we do a comparison of the results that we see here to data taken directly from the commercial version of this LED, we can see that the ASAP results in conformal radiometry agree almost exactly with the performance of the actual device. These are just a couple of ways in which conformal radiometry can provide both qualitative and quantitative information to users about a wide variety of surfaces regardless of their geometric shape.